We'll be continuing with the topic logarithm, and today we want to see how we'll be checking the value for logarithm, the value for the logarithm. The first thing we're going to do here today is this, reminding us of where we stopped in the last class, where we have that whenever we have a number a, it equals to b raised to the power of n, and this we can interpret it to be when we have log of number a in base b to equals to n. Don't forget this because it's very crucial for us. And I remember that I left something open for us last week when I said if we have 7 equals to 2 raised to the power of n and we have to find n, how do we do it? I said we're going to find the log of both sides. Log 7 equals to log 2 raised to the power of n. Log 7 equals to log 2 raised to the power of n. From the law of logarithm that we have studied earlier, this will return to n multiplied by log 2. Then from here we're going to have our n, making n the subject of the formula now. N will equals to log 7 all over log 2. If you notice carefully, you will discover that I do not put base to my log here. I do not put base here. There's no base all through from what I'm doing now. The reason is because at this point I want to work with common base. The common base that we used to work with actually is base log in base 10. We work with log in base 10. And for values of log in base 10, we have a standardized table from which you can check the numbers of log of any numbers in base 10. So the simple thing we're going to do here to find our n is for us to look into our fourth table to find what the log of 7 is, and look into our fourth table to find what the log of 2 is from our table. And that will be the foundation of what we'll be doing today. Now, in WIEC curriculum, anytime you see log and there is no base in it, that actually is telling you that that log is log in base 10, except in the situation where you have the base. If they do not put a base, that is telling you that the log is in base 10. I will refer to that, I said it earlier, that I will call it common logarithm. We have another one which we use so often in mathematics, that is log in base e of a number. We call this natural log. We're not going to be needing this for the curriculum of WIEC. No, we will not get to this for the curriculum that we need to face in WIEC. Okay. For us to find the log of a number, if I say log of a number, log a, let a be any number, there are some certain things that we need to know that will make us to know how to find the log of a number. There is always a two parts to what our result will be. Log a will equals to the first part dot this other part. I will define them one by one. This first part actually is the one we refer, I call it integer. It's a characteristic that we call it characteristic of the log. And this other part is the one we call the decimal fraction, and the name is mantissa. So we have both the characteristic and the mantissa. That is what makes up the log of any value at any point in time. Now, if we have log a, our characteristic is going to be from the number a itself. We're going to get what our characteristic will be from the number a itself, when our mantissa is what we're going to look up from our standard table. Get me again. The characteristic is going to be a value we're going to deduce from the value a itself, and the mantissa is what we're going to be getting from the table, from the standard table we'll be working on. Now, here it is. The integer part is a power of 10 when a is written in standard form. So whatsoever we're going to have here as our characteristic actually is the power of 10 when our a is expressed as a number in standard form. And the other part, the mantissa, is what we're going to be getting from the table. We need to note this. Please note this. They are very, very crucial for us to be able to work out and find out the value of logarithm at any point in time. Examples. If we were to find log 208.5, let's start with the solution of a first. We want to find what log 208.5 would be. Remember, I said we're going to find this 208.5. We need to express this number as a number in standard form, and simply that would be 2.085 times 10 raised to power of 2. So to find log 208.5, it's simple. What we need to do, that will equals to the first part, which will be the characteristic, will be the power of 10 here. And what's the power of 10 here? 2. So we have 2 points. Now the other part of the work now is for us now. Do not mind this decimal point again. Do not mind the decimal point again. What we have now is just take the whole number all together as 1. Then we're going to find, in the log table, we're going to find the column where we have 20. We'll go straight to the row under it where we have 8. Then we're going to add a difference under 5 to it. I'll take that again. We'll go to the column where we have 20 and the row where we have 8. Column 20, row 8. And we'll go to the row where we have 5 also. Whatever we have there also, we add to the value that is under column 20, row 8. And in this situation, in column 20, row 8, we have 318. And in row 5, under the differences, what we have there, we have 11. Sorry, 3181 is what we have here, and we have 11 here. So we add these two together, and that will give us 2913. So what we're going to have here now, the mantissa is 3192. So log 208.5 equals to 2.3192. Again, I'm taking that again. Log 208.5 equals to 2.3192. I would also like to show you how to find this value in another manner, in another way. Look at it. We are looking for log of 208.5. We are looking for that log, which is the same thing as equals to, writing this number in standard form is going to be log of 2.085 times 10 raised to the power of 2. According to those things that we have studied earlier, law of logarithm, if we have a situation like this, what do? This will equals to log 2.085 plus log 10 raised to the power of 2. Is that clear? Do you understand that? Beautiful. Now, you know that log, this natural law, this common law is in base 10. And if it's in base 10, this, let's quickly look at this. Let's look at what this will be. If that log is in log 10, in base 10, log 10 in base 10 raised to the power of 2, using the law of logarithm that we have studied earlier, this will equals to 2 times log 10 in base 10. And what will log 10 in base 10 equals to? 1. So what we have here will equals to 2 times 1, which equals to 2. So the whole of this will equals to 2. All what we just need to do now is to come here and find out what this will be in the log table. I'm not going to mind this decimal point again. You just look at 20 under 8, difference of 5. And 20 under 8 difference of 5 will give us 0.085. 0.3192. Now, let me say this to you that, we have reduced this number to number between 1 and 10. And we know that log 1 equals to 0, and log 10 equals to 1. So, if we have reduced this number to number that is between 1 and 10, that means the log of that number actually also will be a number between 0 and 1. So always the value, whenever we are doing it in the standard form like this, the value actually will be between 0 and 1. The log value will be between 0 and 1. So we're just going to add the characteristic, and in this situation the characteristic equals to 2. So we have 2.3192, giving us the same value as we have here. Let's check what we have in B, where we are finding log 32. To find log 32, all we need to do is, on this side, let's write 32 in standard form. 32 in standard form will be 3.2 times 10 raised to the power of 1. Yes. So we have log 32 to equals to, now the first part, which is the characteristic, according to what we have earlier, says it's going to be the power that 10 is raised to. And here, 10 is raised to the power of 1. So 1 point. Then we now go to check in our four-figure table what this value will be. Now here we have 32, just 2 digits. How do we check it? In our four-figure table, we just go to the four-figure table, we go to the column where we have 32, and we check 32 under 0. 32 under 0. And according to the table, 32 under 0 equals to 5051. 5051. If we're going to use what we have on the other side also, log 32 will equals to log of, writing 32 now in standard form will give you 3.2 times 10 raised to the power of 1, which according to law of indices, this will equals to log 3.2 plus log 10 raised to the power of 1. From what I explained earlier, we know that this will equals to 1, and we're going to find out what log 3.2 equals to. And note this, that log 3.2 is a number between 1 and 10. That means the log value also will be between 0 and 1. So, you know that will be 0. All what you just need to do, ignore the decimal point and find out what we have in column 32 under 0, which also will give us 5051. And this equals to 1.5051. Example number C. We have log 6.45. We're going to write the number in standard form, and 6.45 in standard form is 6.45 times 10 raised to the power of 0. So we know that the power of 10 here would be our characteristic, that's 0 point. Then we now look for the in the log table. We're going to find 65, the number where we have the column 65 under row 5, and the value we're going to have there is 8089, and that will give us our value. Alternatively, writing it in standard form, 6.45 will equals to this, what we have inside this bracket. And according to the law of logarithm, that's the first law that we treated earlier, this will be log 6.5 plus log 10 raised to the power of 0. Now, from what I've explained earlier, 10 raised to the power of 0, log 10 raised to the power of 0 will equals to 0. And log 6.5, we know that this is a number. 6.5 is a number between 1 and 10. So its log will be between 0 and 1. So that will be 0.8089. Looking it up from the table. And when we add this plus this, it gives us this. And to example number D, where we have log 9. When we have log 9, 9 equals to 9.0 times 10 raised to the power of 0 in standard form. And as well, we know that the power of 10 is going to be our characteristic, 0 point. Then our manchester now, we're going to look up for. Now, what we have here is 9. We're going to look in the column. We're going to look, you will not find 9 in your table. What you're going to see is 90. Don't mind it. Just continue putting 0 if you do not have enough number to look up in the table. So what we're going to do here is we're going to look for 90 under 0. It doesn't matter again at that point. All what that matters at that point is what we have here, the characteristic. So here we're going to look for 90 under 0. Now, 90 under 0 will give us 9542. 9542. So we have the log 90 equals to 0.9542. Or alternatively, log 9 equals to log 9.0 times 10 raised to the power of 0. This is 9 expressed in standard form. And we have log 9.0 plus log 10 raised to the power of 10 according to the law of logarithm that we've treated before. Log 10 raised to the power of 0 equals to 0 and log 9 equals to 0.9542, which gives us this. Yes, let's look at logarithm of numbers less than 1. Logarithm of numbers less than 1. We've looked at logarithm of numbers greater than 1. Let's look at examples. Let's get some examples to drive home that. Examples. The first one I have here is 0.2. We have 0.2 and we want to find the log of 0.2. Just like what we have been doing before. Let's rewrite it. 0.2 will equals to, in standard form, what would that be? That would be 2.0 times 10 raised to the power of negative 1. So if I'm writing log 0.2, that equals to log of 2.0 times 10 raised to the power of negative 1. And according to the law of logarithm, the first one, that as we study it, look at it very well, what we have here, this will be log 2.0 plus log 10 raised to the power of negative 1. So if we have this, all we just need to find out is what log 2 will equals to. Now let's look at what this will be. I've explained it earlier, let me quickly explain it again. If we have log 10 raised to the power of negative 1, and we know that this is a common logarithm, that tells us that the base is 10. That is, we have log 10 in base 10 raised to the power of negative 1. Using all of those laws that we have studied earlier, this will equals to minus 1 times log 10 in base 10. And if we have log 10 in base 10, what would that equals to? Beautiful, 1 is going to be 1. So what we're going to have here will be negative 1 multiplied by 1. And that equals to what? Negative 1. So what we're going to have here now will be minus 1. And from our table, let's look up what log 2 will equals to. Now, what we're going to look up of is going to be, we're going to look at column where we have 20 under 0. Column where we have 20 under 0. And the value we're going to have here is 0.3020. Mind you, we are adding them plus minus 1. Let me put it that way. Plus minus 1, right? So we have 0.3020. We need to remove this bracket. Bracket there is multiplication, and it's going to multiply the signs. Plus times minus. That will be minus 1. So our value here now will be that we are subtracting 1 from this. And the result we're going to add there will be our final result. Finding log 0.2, here we are subtracting this 1 from here. And our result will be 0.6980. Example B, we have log 0.001476. Log 0.001476. It's just like what we have earlier. 0.001476 equals to 1.476 times 10 raised to the power of 1, 2, 3, negative 3. Writing this figure now in standard form. Therefore, log 0.001476 is the same thing as log 1.476 times 10 raised to the power of negative 3. Then, according to the law of logarithm, we have this to be log 1.476 plus log 10 raised to the power of negative 3. By now, you should know what this value will give us. This value equals to negative 3. So we have plus minus 3. Let's look up this from the table. What we're going to look for the table will be 14 under 7 plus the difference we have under 6. 14 under 7 plus the difference we have under 6. And that will equals to 0.1690. So we're going to have this add together, 0.1690. Removing these brackets, plus we multiply minus, and that will be minus 3, and that equals to something. When we calculate that, that will give us minus 2. Naturally, it's going to be minus 2.8310. But we don't have minus log. We don't have negative there. So the way we used to write this minus is that we're going to put that minus here. We'll call it bar 2.8310. Bar 2.8310. Another example here, example C, where we're looking for the log of 0.056. Log 0.056. 0.056 is 5.6 times 10 raised to the power of minus 2. That is this figure now in standard form. So instead of writing it now, we can come and say log 0.056 now is 5.6 times 10 raised to the power of negative 2. Using the law of logarithm, this becomes log 5.6 plus log 10 raised to the power of negative 2. We know this to be minus 2. And let's look up for log 5.6 from the table. We're going to look at column 56 under 0. Column 56 under 0. Column 56 under the 0 will give us 0.7482. And expanding this bracket, that will equals to 0.7482 minus 2. So if we add this up, this equals to minus 1.2518. And like I said earlier, by convention, we put this here by 1.2518. If we are to find the logarithm of a number and we have a value for that, it's also so possible for us that we have that value, the logarithm value, and we are to find that number that we started with initially. And in order for us to do that, it's just the reverse of the operation we have earlier. And there is another table for that which we call the anti-logarithm table, which also will help us in this. Now there is something we need to note that will actually help us so well. When finding an antilog, look up the fractional part only. Mind you, when we are working with logarithms, the only part we are looking up from the table is the mantissa part only. We are not looking for the characteristic. It's the number itself that will tell us what the characteristics will be. Now, also, if we want to find the antilog, all what we need to look up from the table is the fractional part only. And the integer, the characteristics now will tell us where we're going to be placing our decimal point. It's just simple, the reversal of what we did when we were looking for logarithm. That is what we're going to do. Let's look at some examples to drive home our points here. Example 1, we're to find the antilog of these following numbers. If we have A, 2.5684, and we are to find the antilog of this number. The first thing we're going to, what we'll be dealing with actually is this value we have here, from here, this value here. We're not going to be dealing with this first and foremost. So in our antilogarithm table, we'll be looking at a point where we have 0.56. The column where we have 0.56, we're going to the row 8, and we add whatsoever we have under difference 4 to 8. And for that, we have under 56 row 8 and difference of 4, we have 3701. That's the value we have, and that will give us our value. Now, in order for us to write the exact expression for this antilogarithm, there is need for us to know where we're going to place our decimal point. And if we are to write this value in standard form, this will be 3.701 times 10 raised to power. The power now that is going to be raised to will be this 2, raised to the power of 2. And that will be the value of the antilog of this number. So in this situation now, what we have now will be 370.1. It's our final value. 370.1 is our final value. Let's look at another one. B. We have 0.2462. I want to find the antilog of this value. The antilog of 0.2462. Mind you, the first, what we'll be working at is this. That is what we're going to look up from the table. We'll be looking at where we have 0.24, the column where we have 0.24, under row 6, and we're going to have the value we have on the difference of 2 to 8. And that will give us 1762. 1762. But that is not the final value. To know what our final value will be, now we need to do as though we are writing this in standard form. And to write this in standard form, our decimal point will be here, 1.762 times 10. What will be the power here? The power here will be what we have here, which is 0, times 10 raised to the power of 0. And the final value here will be 1.762. That's the antilogarithm of this value. We're given the value, 5.639. 5.6391. Okay, 5.6391. And we have to find the antilogarithm of this value. We'll look up this from the table. We'll look at column 0.63 under row 9, and we add whatsoever we have under difference 1 to 8. And that will give us altogether 4356. Row 0.63 on, column 0.63 under row 9, and we add a difference under 1 to 8, and that gives us this value. Now, that is just that. We now need to know what the exact value will be. To know the exact value, we'll write this in standard form. 4.356 times 10 raised to the power of, the power we're going to have here will be this, which is 5. To write the number, the expression in full, that will be 435,600. And that will be the final value here. Guys, let me give one more example. Example D. For antilog, if we're given 1.4962. What we'll be dealing with that we'll look for in the table is 4962. That is, we'll look at column 0.49 under row 6, and we add the value we have under the difference of 2. And the value we're going to have there will be 3134. And to have the exact value there will be 3.1, as though we're writing it in standard form, 3.134 times 10 raised to the power of 1. And in this situation, the final value there will be 31.34.